In this lesson, we'll be moving from physical heat changes into chemical heat changes. We'll explore why some reactions feel warm and others feel cold, and how this connects to the energy stored in chemical bonds. The key idea today is enthalpy, which is the heat change of a process. Presumably, we all know that chemical reactions such as lighting a candle will give off heat and will result in a temperature increase in the environment. In this demonstration, we'll be looking at what happens to the temperature when vinegar reacts with baking soda. A really common misconception is that the bubbling that we're going to observe means that the mixture is boiling, and therefore it means that this mixture is heating up. But as we will see, this is not the case.
Collection. Now, while data collection is going, we're getting a baseline of what the temperature of our vinegar is. After about 10 seconds, I'm going to take some baking soda and I'm going to add it to my vinegar and then start stirring with my temperature probe. And while this is happening, you can see it's a very exciting reaction for the students to happen here. So they should be making also visual observations of what they witness happening during this reaction.
So as we saw, even though it was bubbling, so maybe it looked like it was boiling, it was actually forming carbon dioxide gas, which is what caused the bubbles. And instead of getting hotter, this reaction actually got colder. So we went from 21.5 to about 17.5 degrees C. The fact that it got colder tells us that in order to make the new bonds in the products, we had to absorb some thermal energy from the environment, which means that the temperature probe detected a decrease in the temperature. So what have we learned from these two examples? Sometimes heat is given off during chemical reactions, such as the combustion reaction. This makes it feel hotter. Sometimes heat is absorbed during a chemical reaction, such as the baking soda and the vinegar. This makes it feel colder. So what we're looking at today is what causes it to be different. So chemical bonds contain energy. If you're going to break bonds, you're going to have to add additional energy. And when you go to reform those bonds, they're going to release that additional energy. If you add up all the energy in the bonds of the reactants and then compare it to the total energy of the bonds in the products, you should be able to tell whether there is heat energy given off or taken in. So here is a reaction energy diagram for the synthesis reaction between hydrogen and oxygen. So we have energy increasing along the y-axis, and the x-axis is sometimes called reaction energy progress or reaction energy coordinates. You can think of it as just being time, because here we have the reactants, and then later we have the products. So you can see from looking at this that the total amount of energy contained in the reactants is at a higher total energy level than the total amount of energy contained in the products. So if the products contain less energy, that means that energy had to be given off. Notice that we have a little bump in the middle of this reaction energy diagram. This is called the activation energy or energy barrier. All of these reactions are going to have some sort of energy barrier, and it's linked more to the probability of the reactants being able to get lined up properly to form the products than it is to the actual exchange in thermal energies. So if you were trying to get 3 different reactants to all get together at the same time, you would have a much higher energy barrier or activation energy than you would if you just had 2 reactants like we're showing here. So our new term for the day is delta H. This is the change in the heat content. H is actually enthalpy, but most people say just heat because that helps them remember what's going on. And delta anything, as I've said before, is heat content of product, is your final minus initial. So in the case of a reaction, it's going to be the heat content of the products minus the heat content of the reactants. And so in this case, we're going to end up with a negative delta H. So if you have heat being released, it's like you're subtracting heat out of the reaction system. So now let's look at the reverse reaction. Notice that the energy change is the same, but it's going to work out to be, since it's final minus initial, that the sign is going to be different. And that kind of makes sense, because if you want to break down water back into hydrogen and oxygen, you're going to have to add a lot of energy to it. Usually they use electrical energy in order to break down water. So if your products are at a higher energy level, that means that energy must have been absorbed. And so there's our energy level. Now it's going to be the enthalpy change of the reaction plus that activation energy. And we end up with a positive delta H. So some more vocabulary. If heat energy is given off during a reaction, it's called an exothermic reaction. The way most people try to help students remember this is that heat is exiting from your chemical reaction, so it is exothermic. One of the ways you can tell that you have an exothermic process going on is if you mix stuff together and you have a chemical reaction and the temperature increases. That means that you have heat being given off and it's warming up the surroundings. So you have a positive delta T, and you're going to end up with a negative delta H. Be sure not to confuse heat and temperature, because they're going in two different directions here. And then if you're doing the other direction, you have an endothermic reaction. Now the way I've told my students to remember it is that you are adding heat, so heat is entering into the chemical reaction, so it is endothermic. That was the best one I was able to come up with. So endothermic reactions are the ones where, like with the baking soda and the vinegar, you end up with a temperature decrease, so a negative delta T, and a positive delta H, because we're adding heat energy into it. So this next part is an understanding check, and we're going to say whether the following processes are exothermic or endothermic. So the first one is ice melting. So the way you can figure these out is if you say, well, if I have to add heat, it's going to be endothermic. If I want something to melt, I have to add heat to it. So that one is definitely endothermic. Next one is methane burning. Just think about that candle, and you will know that anytime you have a combustion reaction, burning, it is going to be exothermic. So here we have, we're taking solid sodium nitrate and dissolving it in water, and we focus in on the positive delta H. That tells us right away that it is endothermic. For this one, we're taking concentrated sulfuric acid and then dissolving it in water, get a positive delta T, and I'll tell you, this is really positive delta T. I've managed to get beakers of water to start boiling when I was trying to dilute some acid. So that means it's giving off a lot of thermal energy, so therefore it is exothermic. We have water condensing. Now some people might be able to say, oh, okay, well, if I want it to go into a more condensed phase, I have to remove thermal energy because that reduces the amount of kinetic energy. I actually always found it a little bit easier to think about the reverse process. So to go from liquid to gas, I have to add heat. So that means to go from gas to liquid, I have to remove heat. So it is going to be exothermic. Here we have another one where it is essentially the rusting of iron. And we see that we have a negative delta H. So we can tell right away it is exothermic. Then we have the decomposition of potassium chlorate to form potassium chloride and oxygen gas. It's positive, so that means it's endothermic. Another method you can use to predict things is that decomposition reactions are probably almost always going to be endothermic, just because you're having to break all those bonds, so you got to add thermal energy into it. Oops, there we go. And then the last one, we have the sublimation of carbon dioxide. So this is dry ice. And then afterwards we have gaseous carbon dioxide. So we're adding heat energy into it. So that is going to be endothermic. So to wrap all of this up, chemical reactions involve breaking and forming bonds. If you're breaking bonds, you have to add energy, and then the reformation of the bonds releases energy. One of the ways you can remember that, because that always seemed a little counterintuitive to me, is that this whole enthalpy change thing, if you go one way, it has one sign, and if you reverse the process, it has another sign. So breaking bonds, you have to add energy, so therefore when you reform them, it has to release energy. So exothermic, you're going to have a reaction energy diagram that looks like this. It has products at a lower energy level. You have heat exiting, that's just a mnemonic. Temperature rises, and then delta H is going to be negative, less than 0. For endothermic, everything's switched. So now the products that are a higher energy level, the temperature is going to drop, and we have a positive delta H. And then delta H shows the overall heat change of a reaction. So that's it for this one. Thanks for listening.